The truth is that we're in a really critical moment in our planet's history. All of the hottest years on record have all occurred since 2005. Last year, 2020, was yet again the warmest year on record, and we become numb to it after a while.
We're seeing sea level rises, and that leads to more and more climate refugees, people who are displaced because of that and basically have to migrate somewhere else. And that'll obviously have many different consequences, socially, economically, politically.
If we keep at our current emissions trajectory, we're likely to have 3 to 4 degrees warming Celsius this century. To put that in perspective, the scientists of the world think that we can withstand up to 2 degrees.
What's the truth about climate change? I think it's bad. It's not too late to curb a runaway global warming scenario. It's not. But it is dire, and we have to act now.
The Gonzaga Center for Climate, Society, and the Environment is dedicated to bringing our academic mission to bear on the challenge of global climate change, bringing resources and capacity building to the inland Northwest, both on campus and in our region.
All of the dialogue and the debate over the years helped clarify, the ways in which a center such as this is central to a student in a Jesuit environment, to their education, to their program of study. It really does, I think, set up a caring attitude, but also knowledge that is scientific and culturally specific. So I think in those ways it can really make a huge impact.
Gonzaga has a really strong, clear mission identity. The heart of that, as an institution of higher education, of course, is helping to educate students to live and lead in the world that we find ourselves. It matters what we're doing in our classrooms. What are we doing with our students? What are they learning? And then who are those students becoming? What are they doing in their communities as they graduate? And so it's just critically urgent that we use that academic mission to be of service to addressing the challenge of climate change.
We want to have students and teachers get the best knowledge that they can. And climate change is a multifaceted program, right? There's aspects of it that require science to understand, and then there's aspects of it that require our ethics and our personal philosophies and value systems to also tackle that issue. Through my work with Dr. Brian Henning and now the Climate Center, we have a collection of lessons plans now that tie in a lot to especially local climate issues here in the inland Pacific Northwest.
When you're a kid, you get taught that there's not really anything you can do, that other people make your decisions for you, that, what are you, one kid, gonna do and against this huge crisis that seems so scary and so daunting, so sometimes it's easier just to not think about it at all. But I never think that it's lack of passion in young people. I think that it's lack of knowledge. I think that in order to have that passion, it has to be run by some sort of emotion. And so it takes things like the Gonzaga Center to teach teachers how to teach their students about this. Because I think that as soon as you know the effects and you know what our future is going to look like without this change, then you can't not have that passion.
One of the ways that we are supporting teachers and students in instruction is by being really intentional with providing professional development to all of our instructors, but really targeting science teachers to begin with. And that's been part of our partnership with Gonzaga. Gonzaga and the ESD have reached out and really provided robust opportunities for our teachers to continue to grow their own understanding, as well as to develop lessons and opportunities that filter down to our students. And that's something we're really proud of.
I'm really excited for the center to just become kind of a leader within Spokane on this issue and give all these great opportunities to students to learn more, to organize together within Spokane.
Why is now the right time for the new Gonzaga Center for Climate, Society, and the Environment? Because the problem is so urgent. We have a responsibility to respond as an institution using our expertise as faculty members and as teachers and scholars and the passion of our students to help the community, help Spokane, help the inland Northwest to begin to respond, to understand the problem, and figure out how do we go about surviving and thriving in this century.
Good evening, everyone. Thank you so much for joining us tonight. My name is Professor Brian Henning, and I'm director of the Gonzaga Center for Climate, Society, and the Environment. On behalf of the Climate Center and my faculty colleagues, I thank you for joining us this evening. Informed by an abiding commitment to adjust society and care for the planet, the Gonzaga Climate Center serves Gonzaga and the broader Inland Northwest by promoting innovative interdisciplinary scholarship, teaching, consulting, and capacity building on climate, society, and the environment. And this event tonight is an expression of that mission. In the spirit of the Jesuit practice of composition of place, we acknowledge that Gonzaga University resides on the homelands of the Spokane tribal people. This land holds the cultural DNA and the spirit of the first peoples of this place, the people of the river. It is their ancestors who are here and bring forth the power of this place, the knowledge that comes from the land. We are grateful to be on this land and ask for its support as we work to manifest our intentions during this gathering of hearts, minds, and spirits. If you're joining us from other corners of the earth, feel free to mention your own land acknowledgement in the chat. Quick bit of Zoom etiquette before we get started. I wanted to mention that closed captioning has been enabled. You can turn the feature on or off at the bottom of your Zoom window. At present, only the moderator and speaker can unmute themselves, but there will be an opportunity to have Q&A at the end, so be sure to write down your questions. Remember that at any time, you can change the view or orientation of your screen by going to the top right-hand corner of your Zoom window and changing the view to your preference. The chat is also enabled, and you are free to make use of that if you would like. However, should the chat become disruptive, I'll change the option so that the comments only go to the host. Beyond chat, a helpful way to share feedback during the talk is to use the reactions option at the bottom of the Zoom window. Feel free to give a thumbs up now to practice if you like. Finally, our event this evening is being recorded and will be shared via our YouTube channel by early next week. Everybody here who's registered for the event, which is all of you, will get an email with more information when that has been posted. So now, just a bit of context before I introduce our speaker. Earlier this year, the Spokane Sustainability Action Subcommittee released a draft sustainability action plan that includes nearly 70 strategies across 7 different sectors, including buildings and energy, transportation and land use, waste, water, and health and well-being. One of the strategies, number 1.4 in the buildings and energy section, has received a lot of attention, both locally and across the state. It recommends the following, quote, eliminate gas hookups from all new commercial and multifamily residential buildings by 2023, and from all new construction by 2028. This specific provision of the Sustainability Action Plan draft has created significant discussion within our community about whether we can successfully address the root causes of climate change and continue to use fossil fuels such as natural gas, also known as methane or fossil gas. Advocates of climate action have generally been in favor of adopting plans that gradually phase out all fossil fuel use, including methane for heating. On the other hand, Avista Utilities has expressed concern with this idea. In its guest opinion piece, which appeared on May 25th in the Spokesman-Review, Avista Utilities cited a study by the University of California at Davis, claiming that it, quote, confirms that in Washington, electrification of natural gas heating can actually increase carbon emissions, end quote. This discussion over whether to begin making plans to phase out methane for heating has spawned another initiative. A group of Spokane residents have collected enough signatures to propose revising Spokane City Charter, our constitution, if you will, to make it against city law to disallow methane for heating. This initiative will in fact appear on our ballots in November. So, given the confusion and competing claims about the use of methane for home heating in Spokane and whether it will help or harm efforts to address climate change, the Gonzaga Climate Center realized that it could be helpful to inform the public discussion of this important issue by inviting researchers from UC Davis, referenced by Avista, to share their work and discuss what their research says about the likely impacts of transitioning from methane to electricity for home heating. With that, it's my great pleasure to introduce our speaker tonight, Teresa Pistocchini. Teresa is the co-director of engineering at the UC Davis Energy Efficiency Institute and Western Cooling Efficiency Center with 12 years of experience in applied research in energy efficiency and building operation, primarily in the areas of heating, ventilation, and air conditioning. She earned her Master's of Science degree from the University of California, Davis, and is a registered professional engineer in California. Please join me in a big Zag welcome. Thank you, Teresa, for being here.
Great, thank you. I'll try and be as inspiring as the video. I need to show that to my college-bound daughter. Okay, get my screen shared here. Okay, are we good? Brian, can you see my screen? We're good?
Yep, okay. Looks good.
Thank you. All right. So in today's webinar, I will present an analysis of greenhouse gas emission forecasts for electrification of space heating in the residential sector for homes across the United States. First, I would just like to acknowledge the project team, which includes several R&D engineering staff at UC Davis. And I would also like to acknowledge our sponsor, the Natural Resources Defense Council. And I'd also like to thank Peter Gagnon at the National Renewable Energy Laboratory with assisting us in using electricity emissions forecast data, which I'll discuss further. So the objective of this study was to estimate and compare the 15-year life cycle operational greenhouse gas emission impacts for both a natural gas furnace and a variable speed heat pump in a single family home simulated in locations across the United States. A gas furnace burns natural gas, which is approximately 95% methane for heating. In comparison, a heat pump uses electricity to power a compressor-based refrigeration cycle to provide heating, essentially operating an air conditioner in reverse. We forecast emissions for each heating system installed from 2022 to 2036 and then operated for 15 years. Note that we only considered greenhouse gas emissions associated with operation of the heating system and not the embodied emissions associated with manufacturing the system. So in order to complete this analysis, we have to account for emissions from a number of sources that we're analyzing. In this case, the three different metrics we're comparing are carbon dioxide emissions, and then global warming potential on a 20-year time scale and global warming potential on a 100-year time scale. Just to make sure we're on the same page, global warming potential is a metric used to compare the heating impact of gases in the atmosphere to an equivalent mass of carbon dioxide over a specified time frame, in this case, 20 and 100 years. This gives us a way to be able to compare the impact of the release of various gases into the atmosphere. So our CO2 emission sources include, for the heat pump, electricity used to power an air handler fan, and electricity used to power a compressor, electricity for electric resistance heat, which is a backup heat source when the compressor cannot meet the heating load alone. And then we also have emissions, refrigerant emissions associated with leaks, and methane emissions associated with natural gas production used for electricity generation. And so we analyze those impacts. By comparison, for the gas furnace, we have CO2 emissions associated with electricity used for the air handler fan, combustion of natural gas, as well as methane leaks associated with the production of that natural gas, and methane leaks downstream of the meter in the home. Note that we did not include leaks from transmission and local distribution of methane because natural gas transmission and distribution infrastructure leaks are not expected to scale with changes in consumption unless portions of the transmission and distribution infrastructure are completely removed or not constructed in new neighborhoods. So I'm going to walk through all of our assumptions associated with each step of the analysis and then present the results, and then I'm happy to hear comments and take questions. When we're comparing other gases relative to carbon dioxide, we need to apply a value for the global warming potential relative to carbon dioxide. By definition, the GWP of carbon dioxide over any time scale is 1. Listed here are the values applied for the 20 and 100-year GWP for refrigerant and methane. These values come from the 5th assessment report of the Intergovernmental Panel on Climate Change. In the analysis, we assume that refrigerant R410A, which is in use currently in heat pumps today, is in use until 2026. And then in 2026, we assume that these systems will use R32, which has a lower global warming impact. In terms of locations, we ran the simulation for the largest city in each combination of 48 states and 7 DOE climate zones. And this resulted in a combination of 97 cities. Because California was underrepresented relative to its population because it's largely in one DOE climate zone, we also added San Jose and Sacramento for increased resolution of results in California. The analysis did include Spokane and also Seattle in Washington. I'm pointing at the wrong state. And we used TMY3 weather data that we obtained from White Box Technologies for the weather analysis. So in order to summarize the results, we compute population-weighted average results for each of 6 regions that I've shown here. So for example, all of these cities are grouped into a region that we call the Pacific, Rocky Mountains, Southwest, et cetera. To calculate population-weighted averages, we used the 2018 census data. Okay, so in order to do this analysis, we need hourly heating load data for a home simulated in all of these various cities across the United States. We used a residential prototype building model from Pacific Northwest National Labs. We simulate both the 2006 and the 2018 construction years. The reason for this is to look at how the results change depending on the construction properties of the building. The table shows the main differences between the models. You can see from 2006 to 2018, there's a significant increase in insulation in the building. There's a significant reduction in the effective leakage area and infiltration, and there's a significant improvement in the windows. So newer construction has a reduction in heating loads. So we use these 2 models, the 2006 model and the 2018 model, and updated them to run in Energy Plus 9.4. And we also, just to clarify, has a significant impact on heating loads. We used a 68-degree set point during the day and a 65-degree nighttime set back to 65. So since this is a forward-looking study, we selected a high-efficiency furnace option, which was a condensing furnace with a 96% annual fuel utilization efficiency, or AFUE. For simplicity, we sized the furnace at 100 kBtu per hour and assumed to just ensure that the heating load is met in every climate. In some cases, that's oversized, but it doesn't affect the results of the analysis because they're the same, because furnace efficiency is not affected by outdoor conditions. We also include, as I mentioned, the analysis of fan energy use associated with the heating mode only. And the simulation also includes air conditioning, but we do not analyze the air conditioning results. Okay, so by comparison, we simulate a variable speed heat pump. The data that we used to model the heat pump was based on manufacturer extended data tables for a Trane variable speed heat pump that has the ability to run the heat pump down to an outdoor air temperature of 18 degrees Celsius. So the blue lines here show the efficiency of the heat pump in terms of coefficient of performance, or COP, for both the minimum speed of the heat pump and the maximum speed of the heat pump. The orange lines show the capacity ratio of the heat pump for both the minimum and the maximum speeds. The capacity of the heat pump at any outdoor air temperature is the capacity at the rating condition, which is here, the black dots, multiplied by the capacity ratio at that outdoor temperature. So the heat pump can run at any speed between the minimum and the maximum speed required to meet the modeled load. When conditions allow, the heat pump runs at a lower speed to achieve a higher efficiency. For colder outdoor air temperatures, the COP starts to approach 1, which is the efficiency of electric resistance backup heat. When the heat pump at maximum speed cannot meet the load, the electric resistance heat works in series with the heat pump. At negative 18 degrees Celsius, the heat pump switches off and the entire load is met by the electric resistance heat. The simulation auto-sizes the heat pump capacity in every climate simulated at 1.4 times the design day cooling load, which is a typical method for sizing heat pumps. We experimented with different heat pump sizing methods, but found that increasing the heat pump size to meet large heating loads generally provided minimal benefit. This is because on the coldest climates, on the coldest days, the outdoor air conditions are below that negative 18 degrees C switchover temperature, such that the electric resistance heat has to meet the load alone. You can see how the heat pump cooling capacity and electric resistance capacity were sized in all of the cities simulated. So as the outdoor design day temperature decreases, the capacity is larger, and as the electric resistance capacity is larger, and as the outdoor air temperature increases for the cooling design day, the heat pump size increases. And what's significant here is that you can see that the heat pump was smaller in the 2018 construction year because the building loads are lower. So here you can see the results of the simulation for the fraction of heat provided by the heat pump mode and the electric resistance mode in each region. The dark orange bar is the fraction of the heat provided by the heat pump mode. The remainder is the electric resistance heat. The hatch bar is the fraction of electricity for heating used by the heat pump mode. And the balance is the electric resistance heat. So the fraction of heating provided by the heat pump mode was the lowest in the coldest climates, the Midwest and the Northeast, where approximately 80% of the heating capacity was provided by the heat pump and 20% was provided by the electric resistance. And as you can see, even though that the loads are significantly different between 2006 and 2018 home vintages, the percent of the heating provided by the heat pump is similar because the heat pump capacity was auto-sized to meet the design day load of the home. So here's really the crux of the issue. In order to determine the carbon dioxide emissions associated with end-use electricity consumptions, we used a recently released data set from NREL called Cambium. I can never say it. In this data set, NREL published a long-run marginal emissions rate, which is an hourly forecast from 2020 to 2050 by state. The long-range marginal emissions is defined as a mixture of generation that would serve a persistent change in the electricity system and takes into account structural changes in the grid in response to that demand. So this is an appropriate model to use for heat pump adoption because it's expected that there will be a persistent change in load if heat pump adoption increases across the US. So it's important to note that this long-range emissions rate is significantly lower than what's called the short-run marginal emissions rate, which WCEC also generated results for in an earlier study that is cited in that comment by Avista, or in that policy piece by Avista. And so the short-run marginal emissions rate calculates the emissions for a change in load on the existing grid today and does not allow the grid to expand to meet permanent changes in demand. In my opinion, these long-run marginal emissions rates were just recently developed and published within the last year. And so now that we have this forecast, I believe this is the most appropriate metric to use when looking at the impact of adding load to the grid, such as heat pumps. So just more information, the NREL long-range marginal emissions rates are based on what they call their standard scenario report, which essentially is a conservative forecast for emissions based on state level legislation passed as of June 30th, 2020. The mid-case scenario does not consider any policy goals, including like city, county, or municipal goals, unless they are legislated by the state. So in our analysis, we apply their low-cost renewable scenario, which better reflects the existence of policies that encourage additional renewable growth beyond state-level legislation. The low-cost scenario that we use forecasts that renewables will provide approximately 70% of electricity produced in the US by 2050. So the goal of this slide is just to show you how the long-range marginal emissions vary by state. This shows the average long-range emissions over a 15-year period by state and by region. There's fluctuation in the emissions by hour of day and time of year, and that's all considered in the analysis, but I don't show that detail here. So you can see that, for example, the Pacific region and the Northeast have the lowest forecasted long-range marginal emissions rate, and that it's higher in other regions of the country. You can see that for looking at the analysis that the Pacific region is fairly consistent across states. Okay, so switching back to emissions for direct CO2 emissions, the other emission source we have to take into account is just combustion of natural gas. And that's a very simple calculation. And that combustion value we obtain from the US Energy Information Administration. Okay, so leaving CO2 emissions and talking about emissions of other gases. One of the issues with heat pump adoption is the concern of additional refrigerant being used beyond what is being used for air conditioning today. Providing heating with heat pumps instead of furnaces increases refrigerant use in two ways. First, we have to account for all the refrigerant used in homes that do not have air conditioning. Second, we have to account for the incremental increase in refrigerant in heat pumps compared to air conditioners of the same capacity as a result of some of the additional components that heat pumps contain, such as additional valving and possibly an accumulator. In order to estimate the fraction of homes without air conditioning in regions of the US over time, we forecast the expected air conditioner adoption in the United States by region based on the most current data published by the EIA in 2015. So you can see that we forecast, for example, in the marine region has the lowest penetration of air conditioning. This is essentially the Pacific coast and includes Seattle. For reference, Spokane is part of the cold region shown here in the purple. So next, we estimate refrigerant charge for an air conditioner and a heat pump. We reviewed manufacturer data for comparable air conditioner versus heat pump models for split systems, for residential split systems, 3, 4, and 5 ton of a range of efficiencies, 14, 16, and 18 SEER. Now, one of the things that's tricky is when looking across manufacturer lines, there is significant variation of refrigerant charge among similar pieces of equipment, suggesting that manufacturers don't necessarily design to minimize refrigerant charge. And so what we did is we took an average for all 9 air conditioners and 9 heat pumps that we surveyed, and we arrived at an average charge of 0.28 kilograms per kilowatt of cooling capacity for air conditioning and 0.34 kilograms per kilowatt of cooling capacity for a heat pump. So for the fraction of homes without air conditioning, we consider the full charge of the heat pump as potential leakage. For the fractions of home with an existing air conditioner, we just attribute the additional charge increase for the heat pump as a potential impact of electrification of heating. Okay, so we use data from the US EPA to estimate the annual refrigerant emissions as a function of initial charge. Refrigerant emissions rates are estimated based on some refrigerant loss at the time of installation, some loss for operation of the system, and then some loss at the end of life at removal. We've taken all that into account and estimated a loss rate per year, which is 7.5% per year, which declines based on the the date of installation past 2020 because we assume that there will be improved manufacturing, installation, and operation practices with time. As I mentioned, we assume that R410A is used until 2025, and then R32 is used 2026 and later. And switching gears to methane emissions, to estimate production stage methane emissions, we used a study published recently by Georgia Tech that estimates methane emissions for each state as a percentage of end-use consumption. The reason that we look at this on a state level is that there are several production basins for natural gas across the nation, and their leak rates vary significantly. You can see leak rates are estimated to be the highest in the Southwest and lowest in the Northeast and the Southeast. For gas furnaces, we also apply data from a CEC study that estimates 0.5% of methane emissions are lost behind the meter in home distribution systems. And it's important to note that some of the behind the meter leaks may still remain with the heat pump installation if other natural gas appliances remain at home. As I mentioned earlier, we did not include losses associated with transmission and distribution because we expect those pipelines will have to remain in place and remain pressurized regardless of the amount of natural gas used in a particular home. The exception to this might be entire neighborhoods that are built without natural gas infrastructure or are completely electrified and natural gas infrastructure is removed. Overall, transmission and distribution leaks are generally estimated to be significantly lower than production emissions, so we do account for the most significant source of emissions here. Okay, as I mentioned, we apply emissions from production for producing natural gas to both natural gas used in a home furnace, but also for any natural gas used for electricity production to power that heat pump. In order to estimate the natural gas used by power plants, we pull the cadmium data that I mentioned earlier, which also forecasts the fractional electricity generated by 3 natural gas power plant types for each hour. Then we applied average efficiencies to each type. This allows us to estimate the methane emissions for natural gas production leaks for each. For the end use I've shown here the modeled efficiencies for each power plant type that we assume. Note that natural gas power plants generate only a fraction of the electricity in the 2020 to 2050 forecast, and their production decreases over time as more renewables come onto the grid. Okay, so finally, here are the results that we've been waiting for. So here is the 20-year global warming potential for the home in the 2006 construction year and the 2018 construction year. There are 3 bars shown here on the left for the gas furnace, and here on the right for the heat pump. There are 3 installation years shown, 2022, 2028, and 2036. So for example, we can see here that for the gas furnace, the black bar is the electricity used by the air handler fan. The dark orange bar is the natural gas combustion. The light orange bar is the CO2 equivalent natural gas production leakage. And then the peach bar is the CO2 equivalent natural gas behind the meter leakage. For the heat pump, we also have CO2 generated by the electricity used by the air handler fan. We have the CO2 generated from the electricity used for the compressor, and then finally for the electric resistance heat. And then the yellow bar is the refrigerant, the CO2 equivalent refrigerant leakage. And again, the light orange bar is that natural gas production leakage associated with powering those natural gas power plants, generating the electricity for these black, dark blue, and light blue bars. So we've tried to be as thorough as possible and account for every emission source. So you can see here 2006 to 2018 construction years, the results are remarkably similar in terms of pattern, but you can just see that the emissions we estimate is about half. And that's why, in addition to thinking about electrification, just general building envelope improvements are so important because then the scale of the emissions drops significantly. So I show this very similar result here, except for the 100-year global warming potential. And what's different here is that the CO2 emissions, the direct CO2 emissions are exactly the same as in the previous slide. What's different is the GWP, the methane and the refrigerant emissions have less of an impact on a 100-year timescale relative to CO2. So the results change slightly, but overall the trends are the same. Okay, so now what I have here are some results broken down by region. And so this is the CO2 emission reduction for each region, basically the reduction between a gas furnace and a heat pump calculated for every installation year from 2022 to 2036 that we analyzed. And so you can see here that the results are significantly different by region. The average US result is in the range of 40 to 50% CO2 reduction for a heat pump installation. The Midwest is lower. The Pacific has the highest savings impact. And I aggregate the results by region. Spokane is in the Pacific region, but I did go ahead and pull out the actual result that we obtained for Spokane, and it's in the range of 62 to climbing to 68% in Spokane. And what's also really interesting is that these plots are not identical, but they are very close. We essentially generate almost the same result regardless of the year of construction, meaning that the absolute emission reduction will change depending on the building envelope, but not the percentage savings that we would expect. So I show the same result here for GWP 20. So when we include the refrigerant and methane in the analysis, the savings go up. Again, highest in the Pacific region, 70 to 80+%. The savings for Spokane were right in line with this Pacific average, 76 to 81% is what we found. And then finally, GWP 100, again, highest in the Pacific. It falls in the middle of the, as you would expect, in the middle of the CO2 and the GWP 20 result. Okay, so just to be transparent on just some discussion items and limitations of the study, we found for replacing a gas furnace with a heat pump based on those long-range marginal emission factors we applied, significant emission reductions in all regions. I should say that these regional averages, we didn't simulate every climate in the US and every city and every possible scenario. And some of these regional averages don't necessarily apply to smaller cities, which may have like more extreme weather conditions. Like we looked at some of these very large cities. And results are very sensitive to forecasted emissions for end-use electricity generation. So obtaining these types of savings depend on the changes in the grid to happen that are essentially forecasted and expected. And as I mentioned, long-range emissions that allow the grid to expand give you very different results than short-term emissions on the grid like today as it stands right now. Improvements to heat pump controls. One of the very interesting things about heat pumps is that their efficiency varies based on outdoor weather, that improves as it gets warmer outside, and the grid is constantly, the emissions of the grid are constantly changing. So one research taking place currently at our center is how to, for example, take an emissions signal from the grid and use that to influence your heat pump decision. So run your heat pump at times when more electricities are renewable and store some of that heat in your thermal mass, essentially allow your building set point to fluctuate, not a lot, but a little bit. And so heat pump load flexibility controls could actually improve emissions reductions over what we've shown here. As I mentioned, this issue of heat pump versus air conditioner refrigerant charge is widely variable and is not currently optimized by manufacturers. We see that as a potential research area, just reducing refrigerant charge in general. And as I mentioned at the beginning, we did not, we only include operational electricity consumption and greenhouse gas emissions. We don't look at operational costs over the lifetime of the system, and we don't look at embedded energy from manufacturing. And I think that's it.
Wonderful. So if you want to stop sharing for a second so we can see each other a little bit better, Teresa, before we turn to questions from those participants who are with us, I want to just see if I can repeat back what I think I'm understanding you saying, and you know, correct me if I'm misunderstanding. So it sounds like you're saying that over a 20-year time horizon in Spokane, there would be a 62 to 68% reduction in emissions, shifting from a gas furnace to a heat pump over that 20-year period. And so, am I understanding that part correctly?
Yeah, we look at the date of installation. Let me just go. Sorry if I just go back to that slide real quick. We look at the installation. So this is if you installed a heat pump in 2022 and you operate it for 15 years, we would expect that savings in the Pacific region to be, let me just go back to CO2. The CO2 emission reduction we expect to be, you know, in the Pacific region in general, like the 76% range, for example. 76 to 81%, I think you said. Yeah. Right. And so that's for heat pump installed in 2022 and operating for 15 years. We expect to get better, right? So for a heat pump installed in 2036 and operated for 15 years, you would have a larger improvement because the grid is improved, and we expect heat pump technology, we expect less emissions. So there's another way of putting this point in the discussion. When Avista claims today that it could increase emissions in switching from natural gas to a heat pump, am I right in understanding that could be true if we're looking at the way that electricity is currently produced on the grid in 2021, but would be maybe not true as time goes forward and coal is removed from our grid and other changes are made regarding the Energy Transformation Act, other state legislation. So it becomes increasingly untrue. Avista's aiming to have carbon neutral electricity by 2027 as a company, and has to by state law and by 2030. So is it one of these situations where it's true today but won't be true a few years from now, or how would you characterize it? The issue is this concept of a short range marginal emissions, meaning like as heat pumps start to get installed, there will be additional demand. And so the utility will now have to add generators to meet that demand. If you look at some of the lowest cost power generation sources there and state policy, those are generally some combination of renewable sources and natural gas, and we're going to see coal phase off the grid. So the short-term marginal emissions rate is a calculation that says if the grid cannot expand, if we have to use exactly what we have today. And so it's like a snapshot. Those emissions rates that we used in our first study, I think was based on 2018 or 19 historical short-term marginal emissions rates data. So that wasn't even today, that was 3 years ago. So, but we know that short-term forecast is inappropriate to continue using because we know by state law in Washington and in other states, Oregon and California, that they're mandated, shift to renewables for electricity. So it's the long-term forecast that would indicate that it would be a considerable savings of emissions, as the chart in front of you shows. Am I understanding that correctly? Yeah, I think that's a fair characterization. Okay, thank you so much. That was one of the key points, and we can loop back to that. But I think maybe we'll go to questions in the chat. Before we do that, just a little bit of orientation here. You have some options, everyone, as far as how you'd like to participate. So one idea is to do what some of your colleagues have done, and that is to pose a question in the chat. What I'll do if you pose it there is that I'll read the question,
and Teresa can answer as she would like. A second option is you can click on reactions at the bottom of your screen. And at the bottom of the little window that appears when you click reactions, it says raise hand. And so that will create a queue in the participant window, and I can call on you and invite you to unmute yourself and ask a question yourself. And so we can go that route as well. A third option, if you're feeling shy, but you want to ask a question, you can pose the question to, if you go to the chat and you pose it just to the host, then you can pose it to me and I will read the question anonymously, and we can do it that way. So you have three ways at least that you can participate. I'll start with David Camp's question. In calculations for cost per kilowatt hour in Washington, do you include our new cap and trade pricing of carbon driving up gas prices over time?
Yeah, I see a couple comments about cost here, and a limitation of our study is that we did not analyze operational costs. And so we don't even get at the issue of, all we're looking at here is climate impacts. We don't get at the issue at all of what's it going to cost you to operate a heat pump versus a furnace. It's an interesting question, and it's complicated to analyze because utility rate structures vary so much all over the country, and it certainly is something that could be done. We have not done it, just to be
to clarify
direct.
One point that's it's also embedded in David's question is, am I right in understanding that the study does try and account for changes in state law up to the point at which you stopped, you sort of analyzed? Did you look at different state laws in terms of clean energy standards, for example, things that would affect the trajectory of emissions in that state? Yeah,
and NREL, this is like a 400-page report they have to go with their data set. So we took their data and combined it with our building models and crank out an analysis, and we're essentially relying on their data set and all of the assumptions that go with their data set. And so I've tried to summarize those here, but it's a whole research area into its own, for sure.
One of the things I was thinking we could say in response to David's question is that since the cap and trade pricing, if there was any impact, the study couldn't have looked at it because that just happened a few months ago in Washington state. So we just barely passed that law in April.
Yeah,
and so obviously that wouldn't be included in your study.
Yeah, NREL considered in the data that we used all policy implemented up to June 2020 at the time. And I think there'll be like an updated data set coming out soon.
Gotcha.
Yeah.
Would you say Amy Wheelis's question is similar? Are there costs per kilowatt hour average, or do they account for any tiered rates?
Yeah, again, we didn't analyze. In order to do this correctly, like if you wanted to analyze costs, you would really need to look at, if you really wanted to do a really good job at this, you would have to pull, different utility rate structures for different cities and regions, and you would have to look at hourly impacts of, time of use schedules and whatnot. So it's
not included. Okay, thank you.
Yeah.
Claire Richards asks, what is the difference in reduction for summer cooling versus winter heating? Seems like that would make a difference, as we may have more heat waves and currently less penetration of air conditioning in the Pacific Northwest compared to the South.
Yeah, so certainly there are going to be significant global warming implications associated with an increase in cooling because of climate change, and we don't discuss that or analyze that in this study. We're only looking at sort of the implications of heat pumps as it pertains to heating, other than to say, if we're adding a heat pump to a home that would not otherwise have air conditioning, we need to be careful that we account for all that refrigerant, because that home wouldn't have had refrigerant on site if we had not added that heat pump. Now, because of the climate, the air conditioner adoption rates are increasing fairly rapidly, maybe with the exception of just the Pacific Coast. And so it's becoming like more rare that you have a home without air conditioning. And so, but we're just talking about that, like the issue associated with air conditioning is not really a question that's relevant to is it, more climate friendly to heat with a heat pump or furnace, right? That's a bit of a separate issue. So we don't look at that here.
Gotcha. So Jean Blair says, go ahead.
Oh, there is a question here that's your direct message that might be interesting for the group. A person says that they want to have a heat pump installed, but she's been told by some HVAC technicians that she needs a dual fuel setup. And what that is that is a heat pump where the backup heat source is gas. So I show here, like, this is the load. Go back and oh, I'm past it. So some percentage of the load can be met by the heat pump, but at times it's going to be too cold for the heat pump to provide all of the capacity to the house. And so now you need some backup heat source. And so generally speaking, that's electric resistance. Like, basically it's just a heating element. You run electricity through a coil and generate heat. Why this person might be being told this is because maybe they don't have enough electricity at their house. Like, the panel might not be sufficient to provide that electric resistance backup heat. And so a dual fuel system is a middle ground. We don't show it all here, but you would also expect to have it. The emissions savings wouldn't be as good as if you had done a full, electric only installation. But I would say that if a dual fuel setup is what is possible based on your current electricity service, and it's not cost effective or possible to upgrade your electricity service, then a dual fuel is an interesting middle ground.
Excellent. So Jean's question, she's in Western Washington, and she asks, is a heat pump more or less better for the environment than a ductless heat pump?
Yeah, so has heard pros and cons. We didn't analyze that in any great degree. So a ductless heat pump basically is so we analyze in our model, we use a heat pump where you have like one coil and then the air is just distributed to the house. A ductless heat pump, sometimes they're called like mini splits. You basically run the refrigerant to different rooms and then you have a couple of little air handlers in your house. I wouldn't expect, I think it just sort of depends on maybe your particular home and what's more practical from an installation standpoint, in terms of, like, do you have an attic and existing ductwork, or sort of what your situation is. So I think either of those are good solutions, just depending on what your particular situation is.
Sticking to this point about just sort of the engineering side of the practical effectiveness of this technology in Spokane's climate, there's a question about whether or not, and you kind of touched on this briefly, but whether or not heat pumps are effective or suitable for Spokane winters, where it can get below zero for a few days at a time. I suppose in a heating climate that those days are maybe fewer, but I've heard different things from different builders about whether there are models of heat pumps which actually can work. One told me that there are low temperature heat pumps that can work to negative 14 degrees Fahrenheit, not Celsius. This is the regular one, I think, that I'm looking at. Is that about 5 degrees Fahrenheit? What is that temperature in Fahrenheit, since we live in Fahrenheit?
Oh, yeah, sorry. Let's see, I can do that math really quick. You want to know what negative 14 is in Fahrenheit? I think it's
yeah, just for reference, because I think that's really important for our climate.
Here, we can do it offline here. 1.8 times negative, let's see, 14. I can't do math very good when I'm on Zoom.
Yeah, in front of everybody.
Right. Like, I think it's like 4 degrees Fahrenheit, something like that. Yeah. Okay.
So is it true that there are models which work at colder temperatures, but they're not typical? Is that true?
This particular model we're showing here, this is nothing fancy. This is like widely commercially available from Trane. This isn't something super special.
And this is with backup heat resistance,
yes.
Resistance heating. But if you wanted just a heat pump and you wanted the heat pump to be able to work to, negative 4 or 5 degrees Fahrenheit, are there models that would do that, or were you forced to have a model that would have backup heat resistance or dual fuel?
My understanding is there are developments. There are perhaps some products available in some companies that are trying to make these very cold climate heat pumps that essentially don't need electric resistance backup. But like the problem is at some point you're losing efficiency, right? And so at some point it's practical just to use electric resistance. And I think heat pump technology will improve and efficiencies will improve to be able to get higher efficiencies at colder temperatures. But just to be fair in this analysis, I wanted to use something that's not like some cutting edge heat pump technology, right? Like this is available today and should work in all these climates. So my expectation is, yes, particularly within the next 20 years, we will be able to do better than this, and that there are products that are better than this, right? But this is sort of, you know.
That seems really helpful, and that seems really reasonable. So we have a question now. Does your analysis mean that the later we install a heat pump, the more CO2 reduction we will have?
Yes. I don't know that it's not that significant to essentially make it worth waiting, I don't think. But yes, we do forecast that because the grid will improve, the savings will be greater, but you would have essentially lost the emissions that you could have saved, essentially. Like you'll realize them at a later time. And so essentially the sooner you get it installed, the sooner you start saving, essentially, I guess.
So your reductions annually are larger later because the grid is cleaner, but you're losing the saved emissions from those earlier years. So your overall emissions would be higher.
Right.
If you take the entire sum of the years.
Right. I mean, maybe if we like use an analogy, like if I'm driving a car that burns, that gets a fuel economy of 30 miles per gallon, and I could buy a car that gets 45 miles per gallon today, I could start saving. Do I wait to eventually get the car that runs at 50 miles per gallon? Right. These are not huge differences, and we could make like a really big impact like right now. So
that's a helpful analogy.
Yeah.
Tom Party asks, unless I'm skipping one, if I am, correct me. Does the study consider extreme weather events, or is it focused on average weather?
Yeah, that's a good question. So the NREL emissions data was generated using average weather and not extreme weather events. So we matched their emissions data with appropriate weather based on their recommendation. So we're looking at sort of an average forecast over this 15-year period. Extreme weather events could potentially have some disruptions to electricity generation, and that would potentially change, the analysis. I don't think would be terribly significant when we're looking over 15 years, but we did not account for that.
I have a direct message question from one of the participants asks, the 18 degrees C temperature performance for the basis of study train unit is about a COP of 3. Does the study speak to the performance benefit or not between a COP of 3 and the full electric resistance performance? Is it simply a matter of diminishing returns? Seems like you have a way to go between 18C and full electric performance.
Wait, I'm sorry, I don't see that.
Understand that question.
I don't see that question.
Might have just come to me. Let me send it to you directly because
okay.
I'm not following it myself. So I will just send it directly in the chat just to you. So now you've got it. Does that question make sense to you? I think the person knows what they're talking about, but I don't. So.
Oh, here. Let's see. Here we've got let's pull up the chart here. 18 degrees Celsius. The performance is about a COP of 3, 8 degrees Celsius. 8 degrees Celsius is the standard rating condition for a heat pump. It's about 47 Fahrenheit. And does the study speak to the performance between a COP of 3 and the full full electric performance. Yeah, I mean, I think that this curve is considered.
Can you repeat the question I don't think it's clear what the question is yet.
I think
capture it.
Sure. I think the question is, all right, does the study account for the issue that the heat pump performance changes with temperature? I believe is the question that's being asked. And so the answer is yes, right? Like these are hourly weather simulation files. The simulation looks at the load and the outdoor temperature and then calculates the appropriate coefficient of performance, which decreases with outdoor air temperature.
If that was not your question, participant, feel free to raise your hand or send another message.
Then it follows up here, pointing out that there's lots of temperatures below essentially these cutoff temperatures at the cutoff temperature of 18 degrees C. That's where the electric resistance takes over. And then we simulate using all electric resistance to meet the load. So we account for all the electricity that would be used for the electric resistance heat. And that's why in this plot you see here that, like, for example, in the Midwest where it's very cold, 40% of the electricity for heating is the electric resistance and 60 is the heat pump. So we account for the fact that you're going to have to use electric resistance to provide heating in some of these very cold climates. So that's all accounted for in the analysis.
Thanks for clarifying that. I think a few of these are comments, not questions. I'm going to jump to one I think is a question. If I've missed one of somebody's that was a question, please just repeat it. To clarify, Claire asks, to clarify with existing policy, does short-term marginal emissions change as our grid gets cleaner, or are the utilities allowed not to follow the Clean Energy Transformation Act for short-term marginal emissions when their grid hasn't yet expanded?
It's not like I don't believe that there's policy that requires a certain result for short-term marginal emissions. Short-term marginal emissions are basically what the utility uses to modulate their power production to meet demand. And it just depends, like the short-term marginal emissions rate depends on what power generators those utilities are using. So as the grid improves and more renewables come online, the short-term marginal emissions rates will also improve. Like the two things are correlated. The cadmium data also does have a short range emissions forecast. They have actually like a great web tool. If you Google cadmium, it'll come up and you can like look at by state and you can say, show me long range emissions, show me short range emissions, show me, everything. They have like a viewer you can use.
We have another question centering on our cold climate here. It does get very cold. So since we get temperatures below well below the 5 or 6 degrees Fahrenheit that the regular ones are modeling, and so you include the backup electric heat, resistance heating in your model, which is suggesting in our climate with the typical weathers that we get, which includes those very cold, -4 or 5 for a couple of days, perhaps. It includes that, right? Am I right in assuming that it's including that and saying even though the electric resistance heating is less efficient, the emissions are still lower compared to a natural gas furnace over a 15-year period?
Yes, I mean, that was one of the goals of this study, to account for the inevitable use of electric resistance backup heat with, basic heat pump technology that's available today.
So in other words, as long as you had one with electric resistance backup, then, this study is showing what the figures you were showing on the green graph was showing 70 to 80% reductions over a 15-year period in that switch to electric heat pumps from natural gas, yes, even with our climate, or specifically in our climate.
Yes.
Okay. I think.
Yeah, and then there's a comment here. I guess this is a direct one, but just just, concern in the local market that heat pumps don't work. And I mean, it's not really something we've covered, like that they can't work in cold climates, right? I think that that's, probably a general sort of misunderstanding or some, resistance to change or doing something differently, as opposed to like a technical limitation.
That's helpful. So we have a participant who's interested in asking a question. Eric, I'm going to invite you to unmute if you wanted to pose a question to Teresa. Are you able to?
Yeah, I think that worked. I wanted to ask, I've been thinking about getting a ductless split, and I've been thinking air pump and ductless split were the same thing. So I just today learned that this means two different things. Can you say a little bit more what the study addresses versus ductless splits and
So a heat
better?
Well, like I said, that's not, I don't know that I really say better. A heat pump is just an air conditioner running backwards. It's instead of an air conditioner takes the heat from inside, pumps it outside. And then you switch the direction and you take the heat from outside and you pump it inside, right? Even when it's very cold, you can still move heat from outside to inside. And so the question is what kind of like form factor does that take? So if you have a traditional split system heat pump, you have a air handler in your attic and the refrigerant gets pumped to the air handler and a fan moves over the coil, and then you have some ducting that delivers the cooling or heating to your house. Alternatively, another method, the goal being to reduce losses in the duct system, you can just pump the refrigerant to multiple places in the house. So you could have a fan refrigerant. You could have a refrigerant and fan coil in your kitchen and one in your bedroom and whatnot. And so that has lots of names, but sometimes it's called a mini split or a ductless system or variable refrigerant flow. There's lots of names for it. And so those are two different approaches to heating and cooling. You can use heat pumps in both of them.
Would the refrigerant leaks be higher in the split, out of curiosity?
There's no real indication that the leak rate is higher, but you do have more refrigerant, so you have more potential for losses. The reason sometimes that we think of heat pumps like as the same thing as these mini splits are because you can't do gas heating that way. Like you don't have multiple gas furnaces all over your house. Well, I suppose you could, but that doesn't happen. So that's why, like when we think like the split systems always, these mini splits in multiple locations, they basically always use a heat pump for heating. You wouldn't find like a furnace option for that. But you can also still get a heat pump in a traditional sort of format in a split system, if that makes sense. But I don't know that I would say like better or worse. They're like different approaches. I don't have like an opinion on what's better per se.
Thanks, Eric. I just noted when you mute yourself again, then I got to invite you. So feel free to, if you wanted to.
Okay, cool. So just bottom line is this study applies to both kinds of heat pumps.
Yeah.
Okay.
Yeah.
That was.
I wanted to go back to a question I have about assumptions around modeling the methane emission impact, the global warming potential of the natural gas. And so on the leakage question, you were not including upstream emissions because you're assuming that the infrastructure is going to continue to be there. And so the amount of leakage is going to be continuing at whatever rate it is. And so, am I understanding that part correctly in terms of the upstream leakage rate from?
Yeah, I mean, we produce the natural gas somewhere, and then it's got to get to the house, and then goes to the meter. There's this entire transmission system, right? Which we're still going to have, even if we electrify heating in residential, we're still going to have a pressurized natural gas distribution system that will continue to leak to some degree for, industrial buildings, hospitals.
So you
yeah.
omit that part, but you include the leakage at wellheads?
Yes, because we assume that will scale. So like as natural gas demand drops, we will stop, we will reduce production. The tricky thing about transmission is like the leak rate scales with not with production, but or end use, but with pressure. And we still have to keep those lines pressurized until we can actually like dismantle like entire sections of our natural gas.
That's really helpful. So it includes the leakage at wellheads, which is the major portion most likely, and not in the distribution. And that, for the reasons you stated, that actually makes quite a bit of sense.
Right. Okay. It's also in the realm of negligible compared to the production losses.
Right. I think that's what I've heard as well. Okay. That's helpful. Okay. Well, we're starting to run out of questions. Is there any other questions that you'd like to ask? So we've got one more question that came directly, and I'm going to send it to you as well, Teresa, so you've got it there for reference. Was the model using a nighttime setback of 65 degrees Fahrenheit? Doesn't seem like much of a setback. Did that temperature benefit heat pump system, which seems to have a harder time pulling up from colder indoor conditions?
Yeah, I mean, heat pump controls, the way you control the heat pump will affect the result to some degree, but like we actually did play around with that a little bit, and it didn't have as big of an effect as I would have thought, because as you decrease your setback further at night, you use less electricity because you have lower losses from the home. And so that was a significant thing. We were concerned about the sensitivity of how that might affect the analysis, and it wasn't as significant as we expected. So we settled on the 65, 68 based on a modeling reference for residential buildings.
We have another direct message here. When you think about how many degrees of warming is saved, what would the savings translate to? I'm not sure if the question is degrees of climate change.
No, I think.
Or is it degrees of warming saved?
Oh, I thought he was referring to like how much energy do you save?
I think it's referring actually to climate change. I think they're looking at they clarified they are talking about degrees of climate warming in terms of 1 degree, 1.5 degree, 2 degrees Celsius.
Oh, like if you take these savings per home.
Like if we did transition to, I'm not sure if this is the question or not, but I think it is a version of it, and they can correct me if I'm wrong. But if we did transition to, to electric heat pumps with backup electric resistance heating over the next, I forget if we use several different time horizons, but let's say 15 or years or so. Is there a way of modeling what the global impact would that be in terms of American emissions overall, what the savings would be?
I have not looked at that. I mean, certainly you could take these results and generate that analysis. Like if you assume a certain percentages of home adopt this at a certain scale, you can start to get at the large scale emission reductions. I had one more question. Does the study account for transmission and distribution system losses? That's included in the cadmium data, is my understanding.
And I like to see that Jean is putting me on the spot and asks what heats and cools Gonzaga's administration building. It has a lot of square foot and is old. And so I think it uses traditional air conditioners. In terms of heating, I'm pretty confident that it uses natural gas furnaces at the moment, is my sense. Some of our newer buildings, like the Hemmingson Center, is using geothermal, which is a heat pump of sorts as well, in the sense of, but it's taking the heat or from the water, or vice versa. If I understand the system correctly.
From the ground, probably.
From the groundwater
heat pump.
I think it's this closed loop water system. I think I could be wrong about that. It's one of my colleagues who's in engineering could probably correct me if I'm wrong. I'm getting that detail wrong. It is a geothermal system. Apparently, I don't know what I'm talking about. That's entirely possible. But the older building, it is a real difficult thing to heat and cool because was not designed to have ducts, and so they're putting in ducts, and it's got lots of different parts that, so it's a very difficult building to heat and cool. As colleagues who live on the 4th floor know, it's really hard to do. So the question is whether or not, when we're making long-term decisions, whether as individuals or as institutions, about infrastructure, which can have a long life, you hope to keep a furnace or heat pump for what, 20 or 30 years? Is that a reasonable assumption?
Yeah, the DOE recommends like a 15-year, says that the average is like 15 years, but I mean, I've certainly seen them in use for much longer than that. Yeah. So I think that's what they report as the average. I don't know quite how they arrive at that number. I think if anything, it could be
the point is I suppose that these things have long lives. And so when we're looking at questions about when and whether to switch fuels or switch how we produce heat, or you know, in this case, it has long-term implications. Let's see. So I think we should go ahead and wrap up. And if you're willing to put an email address that would be okay for people to send questions, or maybe what I'll do is actually I'll put mine, and then you don't get bothered, and I can collect them. If anybody has additional questions they'd like to try and get answered on this question from tonight's talk, you can email climatecenter@gonzaga.edu. The slides themselves, I wasn't planning on posting. I'd probably, we could ask if Teresa, I don't have her slides, but she could let us know.
I'll send them. Sometimes it's nice to just have them instead of, like, you know, watching the whole webinar.
The whole video. Yeah, the video will be posted. And so that you'll have that, but if you want the slides, then feel free to email me at climatecenter@gonzaga.edu, and I can pass on your question. I also wanted to mention, while I've got you all here, that we are hosting a number of events in the fall. If you go to gonzaga.edu/climate-center events, you can find a complete list of them, but these are some of them on your screen. In particular, I want to draw your attention to the event on October 6th, which is the 3rd annual Spokane Candidates Climate Change Forum, where we will, after the primary election, we will invite candidates for Spokane City Council and Spokane School Board to join us at Gonzaga's Cataldo Globe Room, and they'll be asked questions related to their views on climate change. So with that, I'd like to thank Teresa for joining us tonight and for clarifying this really important topic as we try and figure out how to go about responding to the challenge of climate change, how to heat our homes and our businesses in a way that still allows us to address climate change. It seems to me that we've concluded that the research shows that on short-term marginal emissions, that there could be an increase in emissions from switching from gas to an electric heat pump, but over the next 15 years, there will be a considerable reduction, 70 to 80% in Spokane's climate in transitioning to electric alternative with, you know, a heat pump with electric backup resistance heating. So that's really useful information to inform this public conversation. I thank you all for joining us, and thank you so much, Teresa, for sharing some of your summer with us so we can learn more about this topic.
Okay, thanks so much. Thanks for having me.